So in this video, we're going to be looking at acids, bases, as well as ionic equations as well, right? Now, starting off with our first definition, right, because we need to be able to recall a bunch of different definitions, apply what we know to ideas such as ionic equations, theories of practicals, and then conjugate bases and acids as well, right? Now, in terms of an acid, right, a Bronsted-Lowry acid, which is one theory of an acid, we say that an acid is a proton donor. And so if I were to write the general formula of an acid out, we've got HA over here, and that's going to dissociate, and it's reversible, this dissociation as well, into H plus and A minus itself, right? Now, the extent of the dissociation determines how strong the actual acid is going to be. So about strong acids in that case then, well, a strong acid, a strong Bronsted-Lowry acid, is a proton donor that completely dissociates, and we can actually show the dissociation being complete by drawing a normal reaction arrow. And so let's say if I were to have HCl, which is a good example of a strong acid, I know that's going to dissociate to form H plus and then chloride ions as well. And you can see, right, through use of this arrow, we've shown that we've got a strong Bronsted-Lowry acid. What about a weak Bronsted-Lowry acid? Well, that is a proton donor that dissociates partially. And so if I were to look at in that case then, right, an example of ethanoic acid, which is going to be CH3COOH, I'm going to show the partial dissociation by showing an equilibrium arrow over here, right? I've got a reversible reaction, reversible dissociation, and so I end up with the following of H plus, and then I end up with CH3COO minus itself as well. And so there you can see I've got a weak Bronsted-Lowry acid. The equilibrium is going to lie far towards the left. Now, we can actually describe our acids as either being strong or weak by using the pH scale. And if we've got a strong acid, we say we've got pH that's going to be less than 1. If you've got weak acid, the pH is going to be greater than 1 itself. And the strength of the acid is actually based on the proportion of dissociation in water. So if I were to look at the following two examples over here, we know the equilibrium is going to lie far to the right. Almost all of our acid actually dissociates, whereas with this example over here, only some of our actual acid is going to dissociate itself. So moving on, right, what about bases? Well, a Bronsted-Lowry base is going to be a proton acceptor. And let's say if I were to look at the following example of ammonia, which is an example of a Bronsted-Lowry base that can accept a proton from water, and what it can actually form is a substance known as ammonium ions, right, which is NH4 plus, and then we can actually also form what's left over, which is going to be hydroxide ions there as well. If I were to look at bases themselves, there's two different types of bases that you can get from GCSE. One of them is an insoluble base, right, a base that cannot dissolve in water, and then another one is a soluble base, otherwise known as an alkali. And an alkali is defined in the A-level OCR spec as a substance that releases OH minus ions into solution itself. And so if I were to look at an example, let's say if I've got sodium hydroxide, right, sodium hydroxide as opposed to something like sodium oxide, let's say, is going to dissociate, right, and it's going to release sodium ions as well as OH minus ions into solution as well. And that's what we can see there. Now, let's say if I were to take an acid like HCl and I were to react that with sodium hydroxide, which is going to be aqueous in both these two cases over here, right, we actually form something called a salt, and that's when the H plus of an acid is replaced by a metal ion or a ammonium ion itself. And so we can form a salt over here, which is going to be sodium chloride, and then we can also form some water as well. If we were to look at bases, we can actually describe them in terms of their pH too. And if we have a pH above 12, right, we've got a strong base. If we've got pH that's going to be above 7 but below 12, we know we've got a weak base in itself as well. So if we go back to acids then for a second, right, we've got 3 different types of acids that we need to be aware of, 3 different classifications, and this comes with this idea of polybasic acids, and that's that different acids can release different numbers of protons. Monobasic acids release 1 proton, dibasic acids release 2 protons, and tribasic acids release 3 protons. But remember, this happens in stages where you've got the first proton dissociating, then the second one in sulfuric acid, but then if you look at phosphoric acid, you've got first, second, and then you've got the third one as well. So moving on to our 4 different reactions that we need to be able to know. We know that an acid reacts with a metal to form salt and hydrogen gas as well, and the observations that we can see between the reaction of hydrochloric acid and magnesium to form magnesium chloride and hydrogen is going to be that magnesium actually dissolves, the solid dissolves, and we end up with fizzing as well. Now, the fizzing is actually down to the hydrogen gas being evolved from this reaction itself, and we know that we've got a redox reaction taking place over here, where the oxidation state of hydrogen is going from +1 to 0, it's been reduced, and magnesium is going from 0 to +2, it's been oxidized. If we were to look at the next reaction, we've got acid, HCl again reacting with a metal oxide, calcium oxide, and that's going to form calcium chloride and then water as well, right? You can see over here, right, that we can't actually see any actual state changes in terms of going to a gas, but the solid itself, calcium oxide, is going to dissolve and we end up forming calcium chloride. So there's our next observation there. If we were to look at acids reacting with metal hydroxides, in this reaction we end up with no observations, and so we officially say that there's no visible change or no visible reaction. Nitric acid reacts with sodium hydroxide, and that forms again a salt and then water too as well. If we were to look at acids with metal carbonates, we expect to get salt, water, but this time, because we're dealing with a carbonate, we form carbon dioxide gas. The calcium carbonate solid dissolves, and fizzing is what we see from the carbon dioxide being evolved too. Now you can also see, right, that we're actually forming a salt, and that salt is going to be based on, again, the H2SO4, the sulfuric acid, the H plus in the acid being replaced by a metal ion or an ammonium ion. In this case, it's going to be calcium 2+. Now these four reactions, you need to know them inside out, and based on that, right, we're going to write some ionic equations for these reactions as well. Let's say if I were to look at the following example over here, right, we've got sulfuric acid reacting with aluminium to form aluminium sulfate and hydrogen gas. We need to be able to write a balanced ionic equation for this. Now, I would normally do this question in 3 different steps, where first of all, I would show the aqueous ionic compounds as being dissociated, so I'm going to separate them out, and anything not in solution, right, we show it as undissociated. So in that case, right, I've got sulfuric acid over here, that's going to be dissociated, and I end up with 2 times 3 lots of hydrogen ions, so I end up with 6H+. And then I end up showing the state symbol for that as well, which is going to be aqueous. And then I've got 3 lots of sulfate ions, which is also again going to be aqueous. That's going to react with 2 lots of aluminium, which is going to be a solid, right? That's very important because aluminium on this side over here is going to be as an ion, and that's going to be aqueous as well. We also have, right, being formed 3 lots of sulfate ions. Again, we've got 3 lots of sulfate ions over here. Don't forget the charges as well. And you end up with aqueous, and then you end up forming 3 lots of hydrogen gas, which is going to be a gas as well. Now the next step is to look at what's at either side of the actual reaction arrow and cancel anything with the same substance, the same state and the same charge itself. So in this case, I can cancel the sulfate ions over here with the sulfate ions over here because I've got 3 lots of sulfate ions on either side. Aluminium, I can't cancel that, right, because I've got aluminium solid on the left and then aqueous aluminium ions on the right itself. And then if I were to simplify this down, the simplest ratio is going to be 6:2 to 3. I end up with a full equation which looks like this, where I've got 6 lots of H+, and that's going to be aqueous, and that's going to be reacting with 2 lots of aluminium, which is going to be solid, and that's going to form, right, 2 lots of aluminium ions, which is going to be aqueous, and then I end up forming 3 lots of hydrogen as well, which is going to be a gas. So I've got here now my balanced ionic equation for this reaction itself. So there's step 1, step 2, and then step 3 done there as well. So moving on then, I want you to try the following examples over here. I want you to write balanced ionic equations for the following and write your answer in its simplest possible form as well. So yeah, starting off with the first one, right, we've got over here in sulfuric acid, we've got 2 lots of H+, we've got that in the aqueous state as well, and then we're going to have 1 lot of sulfate ions, and that's going to be aqueous too. And then again, we're going to have, right, because we've got an aqueous substance over here, we're going to have 2 lots of sodium ions, which is going to be aqueous, as well as 1 lot of carbonate ions itself. So what about our products? And in that case, well, we're going to end up with 2 lots of sodium ions again over here, and then we're going to have sulfate ions, which is going to be SO4 2-, and then we're going to have water and carbon dioxide as well. And remember, the states of those is going to be water is a liquid and carbon dioxide is going to be a gas itself. Now what we can do is we can actually cancel out what we've got on both sides of the reaction arrow. So in that case, I can cancel the sulfate ions off, cancel the sodium ions off, and what I'm now left with is that 2 lots of H+, right, is going to react with carbonate ions, and what that's going to form is water, and then it's going to form carbon dioxide gas as well. Yeah, can I simplify it any further? No, I can't, so I know that's going to be the correct answer. Looking at the next one then, so again, I'm just going to follow the method as I did before, where I'm going to take the ions, I'm going to cancel off what I've got on either side. So I've got 2 lots of chloride ions over here, and that's pretty much it. Can't really cancel anything else, and so I end up with the following. And then there's my products as well. And that's a simplified ionic equation for the reaction between hydrochloric acid and calcium oxide. What about the next one? Well, in this case, right, I've got here protons. I've got H plus over here. That's going to be aqueous. And then that's going to have in there as well nitrate ions, which is also going to be aqueous. And what you'll notice is we've actually got quite a lot of aqueous substances that don't really change going from reactants to products in this equation over here. And what that means is when we cancel it down, we end up with the kind of same overall ionic equation for this reaction, which is that we take H plus and OH minus to make water itself. And so if I were to cancel everything, I can get rid of NO3 minus, NO3 minus, I can get rid of Na plus, Na plus, and then what I'm left with now is going to be H plus OH minus gives me H2O.